Okay, hi there, Dr. Matthew J. Trom here. We are in the Down Selection to Preliminary Design module of the EML 40501 course, and by now you should be well into your preliminary design report. The intent for this asynchronous lecture is to describe to you the process of normalizing concepts to enable those down selection matrices. So what we're going to cover in this lecture are these four items. First, I'm going to explain to you what normalization is. Then I'm going to go over the down selection process and specifically how normalization kind of sits within that process. I'm going to give you a linear normalization procedure that I'd like you to use in the 4501 course. And then I'm going to give you an example of how that procedure is applied to just a simple example. Um, Okay, so first we're going to talk about what is normalization. And I've given you kind of a fundamental normalization equation here just so that you can kind of think through kind of the math underpinning how this works. Turns out that in 40501 we're going to use the modified version of that equation, but I wanted to give you the simplified version to sort of give you the foundation. So what is this equation doing and what is normalization? Well, what this equation is essentially doing is it's taking an input of x sub I, where x sub I is part of a data set. Somewhere in that data set, there's a maximum value, which we call x max, and somewhere there's a minimum value that we call x min. And what we're doing is just setting up a ratio between this value of x sub I and the space between x max and x min, right? The distance between x max and x min. And what that's doing for us is it's essentially non-dimensionalizing xi and giving xi a value then somewhere between 0 and 1, right? So xi sub n is the normalized value of x sub I, and that's going to be somewhere between 0 and 1. So I've essentially said that here. So what is this equation doing? This is an equation that gives you the normalized value for x sub I, where x sub I n is the normalized value of x sub I when x sub I is part of a data set with a maximum value of x max and a minimum value of x min, right? So gone through that. Okay, so what is normalization then? So normalization is a data transformation technique and terminology used in statistics. And what all normalization requires is that the data first be stripped of its units of measurement, right? So as I mentioned before, this is an equation that gives you a non-dimensional number, right? So we're going to remove the dimensions and make all of our normalized values non-dimensional. And then second, normalizing rescales all data to a common feature scaling. And often, as is in the case with this equation, that ranges from 0 to 1. Now for EML 4501, we're actually going to use a range from 0 to 10, which I'll describe in detail as we move through the slides. But the place where normalization starts is essentially assigning a value from 0 to 1. Now, why would you want to do this for design? Well, if you think about how a down selection matrix is structured, a down selection matrix is essentially defined by the quantitative metrics which arose from the customer needs. And those quantitative metrics describe things that are very different. So probably in your design processes now, you have customer needs that are related to the size of your product, the weight of your product, the customer experience, the usability associated with your product, the cost of your product. All of those different metrics are distinctly different in terms of what it is that they're measuring, but we needed some way to put them all into the same down selection matrix and weight them all fairly so that the down selection matrix will tell us which concepts are the ones that should emerge and be pursued as prototypes. And so we need to rescale all of that data so that everything is common between either 0 or 1 if we're doing it this way, or for our purposes 0 and 10 when we normalize in EML 4501. The reason, of course, to do this, as I just described, is it enables easier comparison of dissimilar data from dissimilar sources. So all of those different customer needs that are kind of spread out across the available design space, normalization takes all of their different attributes and essentially puts them onto a scale from 0 to 10 and removes any units so that they can all be compared against one another. Now, the final thing I want to say is you've probably heard the term standardization, which is another term out of statistics. In a lot of kind of non technical discussion, the term standardization and the term normalization are used interchangeably. It turns out that that's incorrect, and so I want to make sure that there's a distinction in your minds between standardization and normalization. Standardization is a specific statistical transformation where the data are transformed so that the mean of the data are centered around zero, and the standard deviation of the data is one. So it's a much more specific treatment of the data than is normalization, which just takes a set of data and converts it from whatever scale it happens to be on to a scale of either 0 to 1 or in our case 0 to 10. So don't confuse standardization with normalization because they're different. Okay, so having described now what normalization is, I'm going to just quickly walk you through the EML 4501 down selection process, which you should be familiar with, but with a specific emphasis on how normalization fits into that process. So here is a representative down selection matrix. Now, of course, this is simplified from the down selection matrices that you'll be producing in your preliminary design reports. I only have 3 concepts. You guys will have 12 or more. I only have 3 metrics. That's the minimum number that you can have and still have a viable down selection matrix per the NIMI principle. And of course, I have not put in any of the numbers. I'm just using variables to represent the values that would be here in the weighting factor column, the concept column, the normalized column, and so forth. But I do want to just sort of use this as a template to help guide you through kind of where normalization sits in your population of these variables as numbers in an actual down selection matrix. So the first column is the metrics column. These, of course, are quantitative metrics, and those arise from the customer needs, and those define the desirable features of the subsystem. The next column, these are the weight factors. The weight factors are developed using trade studies, which you should know how to do by now, and they quantify the relative importance of each metric in this particular subsystem. The next are the concept values. Of course, since I've only got 3 concepts, I've only got 3 concept value columns. You guys will have 12 or more concepts, and so 12 or more concept value columns. These arise from the quantification of each of your concepts with respect to the metrics, remember these metrics, relevant to the subsystem, right? So you guys by now should have already gone through the process of doing some back of the envelope and orientation type calculations to quantify how all these concepts stack up with respect to each of the metrics that you've selected for this particular subsystem. That's where those numbers go. Now, here comes normalization. The normalized concept values, these are the normalized values. And again, I'll show you in this slide presentation how to calculate those. The normalized values that come from each of the quantitative concept values. So the concept values themselves that you've presumably already calculated for each of your concepts go in these columns. And then when you normalize them, the normalized value go in the column that sits next door to those. And then finally, there's the weighted normalized concept values. These are the values that take into account the weighting factors and the normalized concept values, multiply them together, basically scaling the normalized concept values by the weighting factor to give you a number. And these numbers then get summed up over all of your different metrics, and you'll have one sum for each one of your concepts, in this case 3 concepts, so 3 sums, and those sums tell you which of the concepts is the one that emerges from the down selection matrix that should be pursued for prototyping. So that's where normalization fits in. It's essentially the second to last step or third to last step in the normalization process. You take the concepts, normalize those values, and then weight those normalized concept values by your weighting factor, sum up the weighted normalized concept values, and that gives you the ultimate value for the concept that you use to select the concept that moves forward for prototyping. So that's how it fits in. Okay. So let's then talk about the normalization procedure. I've got a 5 step procedure for you here to follow. And I should mention here, those of you who have taken DML, the Design Manufacturing Laboratory in the MAE department, this is a slightly different normalization than is used in the DML class, as you'll see here in a bit. And I would prefer you to use in EML 4501 my version of normalization and not the DML version. And I'll explain why kind of when we get to that point. But please do use this version of normalization and not the one from DML, because this is the one that is self-consistent across the entire class. So where we're going to start out with is step one, is any value that's outside the range of customer needs is immediately going to get a normalized value of 0. And this is now why I'm explaining why I'm using my version of this as opposed to the DML version, which is um, we've eliminated at this point, we've done the elimination of impossible concepts, right? That happened at the end of the conceptual design or the concept design report. But we are left with a number of concepts that don't meet the customer needs, right? You guys have done the calculations and they don't meet the customer needs, but they are not impossible. And so we're sort of in this awkward situation of we've got these concepts, they meet some of the metrics, but not all of the metrics, and you probably felt very strongly inclined to just throw them out and get rid of them, but didn't, hopefully, because I told you not to. I told you only to eliminate the impossible concepts. Here's the stage in the process where those concepts that don't meet the customer needs basically get eliminated, right? They get eliminated from the down selection matrix because they get a normalized score of 0. And if you go back here and you put in a normalized value of 0, when you take a normalized value of 0 and multiply it by the weighting factor, you get a weighted normalized value for that concept of 0. And if one or two of these zeros get summed into the final sum, these concepts, even if they're strong in a lot of other areas, are not as strong as the concepts that do not have 0, that have actual values from 1 to 10 in this normalized column. And so therefore, any of the concepts, for the most part, this happens most of the time, any of the concepts that fall outside of the range of the customer needs, because you've put that 0 in for the normalized value, get thrown out. And so this is the stage in the process where that happens. And again, provided you normalize the concepts whose ranges fall outside of the customer needs, so long as you normalize them to 0, they should be eliminated by the down selection process. So here's where that happens. Now you know, you've been wondering. Here it is. Okay, so that's the first step. The next step, after you've basically zeroed out all of those concepts that don't meet the customer needs, is you pick the best value, which in your particular data set for this particular concept is x max, and you assign it a value of y max equals 10. And then you, in step 3, pick the worst value, and you assign that a value of x min, and then you assign its corresponding y min value to 1. So these y values are your normalized values, and these x values are the actual values of the data that you've produced by quantifying your concepts and doing the calculations to determine how all the concepts stack up against the quantitative metrics. So once you have now your data set maximum value identified and minimum value identified, and you've established y max and y min, your normalizing values, then you can use essentially the equation of a line, right? We've generated 2 points, and we're going to make the equation of a line to generate the linear normalization equation. And I should mention, you guys know that I love thermal fluid sciences. I'm an energy thermal fluids guy. Anytime that I can talk about the similarities between design and thermo, of course, I'm going to do that. And so this is a situation where you guys are already familiar with how to do this, because this same equation is the one that's used in thermodynamics to carry out interpolation on the thermodynamic steam tables. So you guys have already done this in a different class in thermo, and we're just using that same kind of linear linear interpolation technique to normalize our values so that we can put those normalized values into the down selection matrix. Okay, I'm right up against my 15-minute stop time here, so I'm going to stop. You guys go take a break, come back in a few minutes, and we'll finish up this presentation then. See you in a bit. Thanks.